Okay, well, good morning to those on the West Coast, good afternoon to those of you joining us from the East Coast, and good evening to anyone joining us from Europe or stations further east. Thank you for joining this, the 33rd of our regular series of short courses on pumping topics. This one, as usual, will last about 40 minutes, allowing us the time for a Q&A session after the presentation. Those of you who have attended any of the earlier sessions will know that we deliberately steer away from product presentations and towards educational content, addressing a pumping topic in each one. And that's particularly so of this particular pumping topic. We believe this is very important in the new world order of many engineers working from home, making in-workplace training that much more difficult. I do, of course, include a few slides at the end of the presentation to remind you of who we are and what we do, but I don't dwell on them, and they'll be in the PDF copy of the presentation you get, so you can peruse them at your leisure. Now let me restart the share and make a start. And here we go. Well, here is a listing of all the previous short courses we've run during the last 3 years. And if you've missed any of them, you can get a copy of the materials by going to www.ruhrpumpen.com and follow the link to RP short courses. Here's where you get to if you go to ruhrpumpen.com, and here is the link to RP short courses. But while we're here, I'll just have a look at this one as well. Select your pump. During this session today, you're going to see curves that have been generated by our curve drawing program, GPS. You can download your own copy from using that link there. But anyway, back to the RP short courses. If you click on that link, it takes you to this screen, where you'll see all of the recent courses listed, and you can click on any of them to see the course material. The most recent of the previous 32 courses are up here. Well, this seminar is going to look at handling viscous fluids with centrifugal pumps. It will look at how to correct standard water-based performance curves for handling viscous fluids, and also the considerations to be taken into account in selecting and specifying them. While manufacturers' curve drawing programs automatically correct for viscosity, it's important to understand how and why it works. Also, it helps to understand how a pump normally operating on oil at, say, 10 centistokes, how it will behave during startup with cold oil at, say, 100 centistokes. Now, I was going to address slurry pumps as well in this short course, but I decided to defer that to another future session, as there's quite enough material, quite enough information to get across on this subject alone. We will, as usual, be holding a Q&A session at the end. It won't be fully interactive. There are just too many of you on board for that, but we will do the best we can. Please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I'll address those that I can live at the end of the session, and the rest we'll address by mail in the coming days. We are recording this session and will make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow and of the Q&A summary from both of today's sessions. Well, let's start by saying, what does viscous oil look like? And here is a link that I'll click on now. I'll have to change my screen share, so bear with me. Okay, here it is. And here we see 4 automotive oils. This one on the right, 15W40, is about 290 centistokes at 20 centigrade. This one, 10W40. There we go, 10W40. That's about 200 centistokes at 20 degrees centigrade. And this one, about 180 centistokes. So you get some idea of how thick and gloopy the presentation. There we go. Just check we are looking at the right screen. Yes, we are. That's good. So, handling viscous fluids, this is the key referenced source. Hydraulic Institute 967, 2010. Effects of liquid viscosity on rotordynamic pump performance. I'm going to take you through this and show you how we, as manufacturers, use it. I've taken extracts from it for the purpose of this educational webinar. If you need to use the content professionally, I would encourage you to buy the standard, as we have done. It's an empirical method based on test data available from sources throughout the world. It provides a way of predicting the effects of liquid viscosity on pump performance with adequate accuracy for most practical purposes. This 2010 version is a substantial update on the previous version from the year 2000. It's taken a lot more data from all over the world, and the new method matches the experimental data better than the old 2000 spec. What does it cover? Well, conventional single-stage and multi-stage pumps with closed and semi-open impellers, kinematic viscosity range 1 to 3000 centistokes, and rates of flow 3 to 410 cubic meters an hour, and with head per stage 6 to 130 meters. Probably prefer it in gallons a minute and feet. Here it is in gallons a minute and feet. There's a caveat here telling you that it can be used outside of these limits, or in other words, outside of these limits, up to 10,000 gallons a minute. And the caveat is that there'll be an increased level of uncertainty, but still a lot better than the old 2000 version. So, what are the losses and why? Well, in any pump, you have mechanical losses, and these will be essentially independent of the viscosity of the liquid being pumped. Then we have hydraulic losses, which are similar to pipe friction losses, and they occur at the inlet of the pump, in the impeller, in the volute or diffuser, and in the discharge of the pump. These hydraulic losses consist of friction losses, which are a function of the Reynolds number and hence of the viscosity. Also, it'll take into account pump size, rotor speed, and surface roughness of the hydraulic passageways. Thirdly, we have volumetric losses, and these are caused by leakage flows through the tight running clearances between pump rotor and stator parts. In other words, between the wearings, between the case and impeller wearings. These leakages decrease with increasing viscosity because the friction factors in the clearances increase with decreasing Reynolds number. Thus, the rate of flow through the pump can be increased, resulting in a higher head. And this shift of the HQ curve caused by reduced leakage compensates, for some extent, to the hydraulic losses mentioned here. Now, this effect may be appreciable for low specific speed small pumps with relatively large clearances when operating at viscosities below about 100 centistokes. This is the most important factor, disc friction. These are another kind of friction loss, and they occur on all wetted surfaces rotating in the pump. The associated power losses strongly influence pump efficiency with viscous liquids. And the disc friction losses increase by a factor of about 30 when the viscosity rises from 1 to 3,000 centistokes. They're generated mainly on the side shrouds of a closed impeller and in devices for balancing axial thrust, so thrust discs, thrust drums. And the losses also increase with decreasing Reynolds number or increasing viscosity, of course. And this demonstrates that efficiency when pumping viscous liquids depends strongly on specific speed, due solely to the effects of disc friction. And the absorbed power is likewise affected. So lower specific speed equals higher losses. This picture illustrates this quite well. Low specific speed pumps have a bigger diameter and narrower flow passages than pumps with higher specific speed impellers like this one or this one. So understandably, the disc friction losses are much higher for low specific speed impellers. Disc friction much higher for these impellers. Pumping viscous fluids will cause the HQ curve to decay like this. This is the water curve, the solid line, and the dashed line is the viscous curve. Likewise, the efficiency curve. Here's the water curve, and here's the viscous curve. And the viscous power curve here will be similarly higher. So how do we calculate the magnitude of these effects? Well, whether you're doing it manually or letting the manufacturer's curve drawing program do it, this is the method that is followed. Step one, you calculate what is called parameter B. Here is the formula straight from the standard. Here it is in metric units, and here in US customary units. Now, this formula and the formulae to follow will be a bit tricky for you to calculate if you're doing it on a cell phone or a pocket calculator, or if you're as old as me, you might even try and do it on a slide rule. But it won't be an easy task. So I've done it for you in an Excel spreadsheet, which I'll show you in a minute or two. But however you do it, you calculate parameter B with this formula. And if B is greater than 40, then stop. This is probably not a good centrifugal pump application. It might be that it's a very small pump and very high viscosity, and that won't be any good. On the other hand, if it's a much larger pump, that will be able to handle the viscosity better. So anyway, the first thing, you calculate parameter B. Once you've done that, you read off the correction factors for CQ and CH from this chart. You go in with the value of parameter B you've just calculated, say it might be 10. And you come up here to the solid black line and you read off the value of CQ and CH. Now, CQ and CH are numerically the same when you're at or near best efficiency point. And as I say, that's the solid line. The dotted lines you'll need a little bit later, and they are for the flow at 60% of best efficiency point, 80%, and 120% of best efficiency points. You'll need those when you actually plot your viscous curve on top of your water curve. You can calculate these two factors, and here is the formula for that. This is how the computer programs will calculate it, and you're welcome to try it with your trusty slide rule, but I think you might well struggle. 2.71 to the power of minus 0.165 times log to the 10 of b, all raised to the power of 3.15. As I say, reading it off the chart is quite accurate enough. We don't need 3 decimal places here. So once you've read off factors CQ and CH, we can calculate the approximate water performance flow and head that we want with these formulae. Then we go ahead and select a pump that has the performance of QW and HW as close as possible to BEP. Then we go to the next chart and we read off the correction factors for C efficiency. Here it is. Again, we come in with the value of parameter B that you've just calculated and read off CF, C eta. If you want to, here is the formula for calculating these, which is how the curve program will do it. But again, reading from the chart is perfectly accurate enough. We don't need 3 decimal places again. Then once we've got this factor, we can calculate the viscous efficiency. Step 6, we calculate the viscous power using the usual power calculation formulae. As I mentioned, I've done a spreadsheet for you, and here is the spreadsheet I've written to calculate the viscosity correction factors. Here for parameter B, you enter the flow, the head, viscosity, and the speed in the grey cells, and the calculated value appears here. Here B, for this flow and head, is 5.521. At the same time, it also calculates CQ and CH. We've got all the information to complete this formula, and it calculates CQ and CH here at best efficiency point, and here at 60% of BEP, 80% of BEP, and 120% of BEP. And scrolling down a little further, we get to the correction factor for efficiency, C eta, CF. And it comes out here at 0.738. I will give you a copy of this with our course materials when we send those out after today's sessions are completed, so in the next few days. So let's do a worked example. We're going to select a pump to deliver 100 cubic meters per hour at 70 meters of TDH for hydrocarbon with a specific gravity of 0.9 and viscosity of 120 centistokes. In step 1, we calculate parameter B using this formula, and here it's 5.7, which is less than 40, so we are good to go. Step 2, we read off CQ and CH from the chart, 0.93 in this instance. Step 3, we calculate the required water pump duty using these formulae and this factor. So we know now that the water pump that will give us the viscous flow of 100 against 70, the water pump we need is 107 against 75. So we'll go away and we'll look through our curves and we'll select that pump based on that water performance. Then we'll go back and we'll calculate the C efficiency. Or we'll read it off the chart is more the point. And we'll calculate the viscous power. Step 7, we will tabulate the data And step 8 will be to draw your viscous performance curve on top of the water curve. Well, if you're doing it manually, you'll prepare a tabulation like this. Here are your givens: the viscosity, the specific gravity, and the speed. You calculated the water performance required as being 107 cubic meters an hour against 75 meters. And in step 3, we selected a pump with BEP as near as possible to that. In this instance, 110 cubic meters against 77. Pretty close to 107 against 75. We're very close to best efficiency point, clearly. From that curve, you tabulate this data at 60%, 80%, 100%, and 120% of best efficiency point. Now, here are the correction factors that you've read off the charts. And here is the calculated viscous performance data for the pump, applying these factors to these this information, again at 60%, 80%, 100%, and 120%. Here is your curve as drawn by the computer. In this case, the Ruhrpumpen GPS selector, which is an IntelliQuip-based tool. Nearly all the pump companies use an IntelliQuip-based system, so we all do this pretty much the same way. The dotted line is the water viscosity curve, and the solid blue line, is the viscous performance. So here we see the water performance, 107 cubic meters against 75 meters. And here's the viscous corrected performance, 100 cubic meters an hour against 70 meters. If you were doing it manually, you would plot the 4 points that you've tabulated here. You plot those points on top of the curve at 60%, 80%, 100%, 120%. We'd plot those points, and then with a flexi curve or a ship's curve, you'd extrapolate this curve back to the origin. Same with the efficiency. Plot these 4 points and extrapolate it back to the origin. And again with the power curve. Here are the performance data sheets from the GPS program. You can see here the calculated correction factors. Here's the data it gives you, and here's the second page of performance data. Now let's have a look and see what happens when we vary the viscosity. This is the example we just did. Here is the performance at 1 centistoke, effectively water. And here it is at 120 centistoke. See what happened to the useful power. Went up from 25 kilowatts to 37 kilowatts. And here it is at 450 centistokes. It's double the power as it was if it were 1 centistoke oil. And that's for 450 centistokes. This is a small-sized OH2 pump. It's a 4 by 3 by 11. That's a 4-inch suction, 3-inch discharge, 11-inch nominal diameter impeller. And here is the curve at 450 centistokes. Quite a big difference there in efficiency and power. Another example, a larger pump this time, an 8 by 8 by 15. So an 8-inch suction, 8-inch discharge, and 15-inch nominal diameter impeller. And this time we're doing it at a much higher viscosity, 1250 centistokes. A 64% higher power when pumping 1250 centistokes instead of 1 centistoke. And here is the curve for that. What about NPSH? How is that affected by viscous flow? Well, there's no definitive answer within the Hydraulic Institute 9.6.7. There are positive and negative impacts of increased viscosity. Here are 3 extracts from the standard. There is a dual influence of the pumped liquid viscosity on NPSH3. With increased viscosity, the friction goes up, which results in an increase in NPSH3. And at the same time, higher viscosity results in a decrease of air and vapor particle diffusion in the liquid, which slows down the speed of bubble growth. And there's also a thermodynamic effect, which lead to some decrease of NPSH3. So some factors increase it and other factors decrease it. The effect of viscosity on NPSH3 is substantially a function of the Reynolds number, but it cannot be expressed by a single relationship for all of the different pump designs and types. So it says, as a general rule, larger sized pumps and pumps with smooth and sweeping impeller inlets are less susceptible to changes in the pumped liquid viscosity. And here's the third extract. Pardon me while I wet my whistle. Gas dissolved in the liquid and gas entrained by the pumped liquid in the form of finely dispersed bubbles influence NPSH3 differently than large bubbles of gas. If the flow velocity at the pump inlet is high enough, then a small amount of entrained gas does not separate and essentially has no or very little influence on the NPSH3. So that's the normal situation. We don't normally have large gas concentrations going through our pumps. So small amounts of bubbles, finely dispersed, no or very little influence on the NPSH3. But the presence of larger gas accumulations greatly affects the pump suction performance. No surprise there. It causes the total head NPSH characteristic curves to change shape from exhibiting a well-defined knee to having a gradual sloping decay in head. And this increases the point of 3% head loss, or effectively moves the NPSH3 to a higher value. Let me illustrate this because it's difficult to take in when you just read it. Here's a typical NPSH curve. Here is the knee that they're talking to in the last slide. So let's take this flow of 402 gallons a minute. And in this test curve, we have here the suction pressure, suction head, which is effectively the NPSH available. And here is the discharge head that we're measuring. So we take a flow of 402 gallons a minute and we gradually reduce the suction head, the NPSH available. And we plot the points while measuring the discharge head. Here are the points, and here is where we get a sudden fall off in discharge pressure that indicates the NPSH3. So here with water, we're seeing a sharp, well-defined knee, and the NPSH3 point is about there. Just go back to the previous slide and read this bit again. Larger accumulations of gas cause the characteristic curve to change shape from exhibiting a well-defined knee to having a gradual sloping decay in head. So instead of being a sharp knee like this, it will gradually decay like that. And that means instead of your NPSH point being here, it could be back here somewhere. A higher value of NPSH. So that's for large volumes of gas. So we see that Hydraulic Institute can't really make up its mind definitively what the real effect of viscosity on NPSH3 is. It does suggest a formula for a correction factor, but it does say the users caution that it's based on an analytical approach and is not based on actual NPSH test data. And so they recommend that when pumping highly viscous liquids, ample margins of NPSH-A over NPSH3 are required, and the advice of the pump manufacturer should be sought. Well, as Ruhrpumpen and most of the other major pump manufacturers, we don't use a correction factor. What we do say is the best advice is be cautious with your NPSH margins. Well, let's look at some other considerations in handling viscous fluids. Firstly, seal manufacturers should be consulted with all process conditions to ensure the right sealing solution. I'll mention a little more on that in a later slide. For sealless pumps, so can motor or magnetic drive, if we're going to be offering those, we as pump suppliers have got a lot of things to consider here. In canned motor pumps, the motor, rotor, and sleeve bearings are immersed in the pumped liquid. And if it's a magnetic drive pump, the shaft magnetic coupling and bearings are immersed in the pumped liquid. So the additional viscous drag due to the immersion of these components will lead to higher losses and result in increased power consumption, increased starting torque requirements. Conversely, heating of the viscous fluid in the rotor chamber will be a mitigating factor, and cooling flow to the motor or magnetic coupling and bearings will be decreased. And the temperature rise caused by the increased losses, decreased cooling flow, need to be considered too. So lots of things that we as manufacturers need to take into account if we're going to be offering canned motor pumps or magnetic drive pumps. And the third important consideration, motor sizing. Make sure that you have considered the maximum viscosity case. And again, I come up with an example where this wasn't done in a following slide. Next obvious question is, what is the limit of viscosity that a centrifugal pump can handle? You'll be surprised to know there is no definitive answer. This standard says you can go up to 3,000 centistokes, but I think you seldom would. If you speak to a positive displacement pump vendor, he'll tell you it's 200 centistokes. You speak to a centrifugal pump vendor, and he'll say 2,000, might even say 3,000. But you saw an example too, what 1,250 centistokes does to your absorbed power. It was 164% of the water viscosity curve power. So I posted this question on LinkedIn on 3 specialist pumping forums. My posts were read by over 700 pump guys, and I got one answer. It was a good one, and I'll show it to you in the next screen. But my own opinion is that above about 500 centistokes, start looking at positive displacement pumps, largely from a cost of power and OPEX viewpoint. Here is the one answer I did get, and it's from that well-respected pump guru, Simon Bradshaw. Has to be something about Simon. We're obviously pump gurus, we Simons. Anyway, Simon made 4 valid points, which I share with you here. For pipeline pumps, the main criteria is OPEX, since the cost of power is their biggest cost by far more than the CapEx. Next, you need to check for potential overstress on the shaft, keys, coupling, etc., and overload of the motor. This is sometimes overlooked on pumps that need to start in really low ambient temperatures. Simon recalls a big refinery BB2 pump for Siberia that had to start under very cold conditions And the short-term fluid viscosity was so high, they had to have a special startup routine to limit the flow to less than 10% of BEP until the fluid got warm enough. Otherwise, they'd have damaged the pump and motor. So that reinforces the point. Make sure that the pump supplier, that the motor supplier, that the mechanical seal supplier knows all the viscosity circumstances when the pump might be operating, upset conditions, startup conditions. His third point was on smaller pumps and low specific speed pumps, it's mainly an issue of predicting the resulting performance. And he says, check Hydraulic Institute 967, the B parameter. And that's what we've been doing in this course up to now. And his fourth point, can the mechanical seal take it? In terms of stress on the components from drag and shear between the seal and the shaft, the traditional drive set screws may well be inadequate. A good point. Here are some typical fluids and their viscosities. You can look online and you'll find hundreds and thousands of these. I just used some of these as typical, and there's nothing too frightening here. All of these could be handled comfortably with a centrifugal pump. But this is a very important point to consider for oil pipeline applications. Crude oils in the 30 to 50 API gravity have viscosity in the range of 5 to 15 centistokes. Very handleable by a centrifugal pump. But over 50% of the world's recoverable crude oil is 22 API gravity or lower. 22, here's the viscosity of those, up in the region of 70 to 1,000 centistokes. So a very different proposition. Thanks to Simon Bradshaw again for this curve. And indeed for this fascinating article by Simon Bradshaw comparing a BB3 multi-stage centrifugal pump with a triple screw positive displacement pump, making the important point to carefully evaluate OPEX as well as CAPEX in such circumstances. There's a link here so you can read this article. Well, that's it for today's session, apart from the Q&A in a few moments. But first off, I just want to advertise the next of the short courses, which will be on fire pumps for the oil and gas industries. As well as covering fire pumps in general, the course will cover engineered fire pump packages for hazardous areas such as offshore oil platforms and refineries. 6th of June, that's 4 weeks today. Again, 2 sessions, one in the morning for the Eastern Hemisphere and one in the afternoon for you guys in the Western Hemisphere. The invitation will be published very soon, so put it in your diary. I am leaving this meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now. Those that need a fuller answer will be answered within a few days. Anything you think of later, email to marketing@ruhrpumpen.com or directly to me at smith@ruhrpumpen.com. Our marketing team will direct your questions to the right people, or they'll be sending you the YouTube recording and the PDF of the presentation, the consolidated Q&A from both of today's sessions, and the correction factor calculation spreadsheet that I've done for you at no extra charge. If you need a certificate of completion for this short course, then send an email to marketing@ruhrpumpen.com. Here, as usual, are 8 slides about Ruhrpumpen to remind you of who we are and what we do. They'll be in the PDF copy that you get, so you can peruse them at your leisure. Now, let's have a look and see what we've got in the Q&A. So far, just two. Let's say, can we use for sludge as well? That is Shima Faraji. Can we use for sludge as well? What's the viscosity of your sludge? You can pump it, you can enter the data into the calculations for according to the ANSI standard and see if you get a calibration, a parameter B figure less than 40. Maybe you can handle it. It depends. Define sludge. Anonymous attendee has said, when we read the TDH off a pump curve, does it really, does it already include or does it exclude the NPSH required? Um, Fundamentally, we don't change the NPSH curve. We don't change it. It's possible if you've got large quantities of gas entrained in the fluids that it will be a higher NPSH, but generally, when you've got only small amounts of gas or developed fluid within the pump fluid, it doesn't impact on NPSH. So just give yourself a bigger margin than you might have done if it was a thinner fluid. Anonymous attendee says, are we going to have a separate session for handling slurries in centrifugal pumps? I believe that was the headline for today's session. Well, yeah, it was a secondary point. I thought I could cover both slurries and viscous flow in the same session. I did 40 minutes just on viscous flow. I didn't have time to do the slurries. I will prepare a separate presentation and we'll do that in a few weeks' time. Anonymous attendee says, are the viscous fluid calcs applicable to non-Newtonian fluids? No, very good question. No, they don't. You can't apply them to non-Newtonian fluids. They're a very special beast of their own. Angelo Mendez says, what would you recommend in the case of a parameter B higher than 40? Change to a higher model capacity or change the technology? I have played with parameter B by plugging in different values of flow and head and viscosity and so forth into my little calculator. And what it really, if you've got a very high value of 40, it's probably a very small pump and high viscosity. And we saw that small pumps tend to be a low specific speed, around about 500 in US units. So the smaller the pump, the less flow, higher viscosity. That's when you get factors of B above 40. If you've got larger pumps that are with medium type of specific speed or into the Francis vein region, then they're far more forgiving and they accept more viscous flow. So then if you've got quite high viscosities and higher flows, that B number comes down. So I think that B number will be higher for small pumps and lower for large pumps. Sunday Azubijo says, hello, I'd like to receive the content of this training in my mail. Okay, we will make sure that you get it sent. Paul Berthiaume says, can you provide a brief history on how the parameter B was developed? No, I can't. I'm sorry, I wasn't on the panel of Hydraulic Institute that did it, and they don't immediately do it. I'll throw a question out there and see if anybody knows, but what it amounts to is the hundreds and thousands of pumps that are pumping viscous fluids. That data was fed back to the Hydraulics Institute, and they've tabulated it and looked at it and come up with these both parameter B and the head and flow correction factors and efficiency correction factors. So it's a big task, and it's been improved over the years. The first version in 2000 was pretty good. The 2010 version is better because they've got more records that they've been able to look at, and I believe, I understand there's a 2021 version, which I don't have my copy of yet. It's still in the post, and I expect we'll see that they've refined very slightly the formulae to reflect an even larger database um, of pumps. Anonymous attendee, is there a standard for the non-Newtonian fluids calcs? I don't know. It's again a very different product. Non-Newtonian fluids are often better handled by a positive displacement pump, and they're less susceptible to. Well, you're not churning them around, so they're not getting thinner as you pump them. Craig Butler says, how does this method vary compared with the correction charts, such as those published in Cameron's? The Cameron data actually predates the 2000 version. So, yes, Stepanov's and Cameron's data, they were okay for their time, but it's been improved as time's gone by with more data. Well, some interesting questions there. Thank you. That's all we have for the moment. Um, just, I'll just wait for a little longer to see if any more questions come up. We've still got a little time. It's still only 10 to 6 here, so I can't unstopper a beer until 6 o'clock. So a few more questions, please. Nope, that looks like all the questions. So it just leaves me then to say thank you for attending today. I've enjoyed preparing and presenting it, these two presentations I've done today. I hope you found them useful. I look forward to seeing you guys again on the 9th of June in 4 weeks' time for the next short course on fire pumps. Take care and goodbye.